in spite of his busy schedule, is on his way to the airport. So Professor Pal, if you could just say a few words to initiate our proceedings, that'd be very nice.
Yeah, thank you, Dibendu, for inviting me. I'm a little bit, I hope there is not much of disturbance. I'm in the airport, as you said.
No, you're
But it's
fine.
my great pleasure to inaugurate this workshop, which is being sponsored under the Spark program of the ministry. I think the Spark program is a very important program of training where the experts from all over the world can come and deliver talks. And this particular workshop on machine learning in space science techniques is very important because space science involves, in fact, space science is one of the two or three, according to me, along with probably biology, the genetics in biology, is one of the two or three subjects, according to me, where the big data analytics is extremely important. And big data analysis really requires a knowledge of machine learning, as well as it can go into the artificial intelligence, though they are not exactly the same. But certainly, machine learning is extremely important. And for the students to be trained at an early stage, and it's going to be a very useful workshop. I can see that there are experts from various institutions in India, uh, and also from abroad. I'm very happy to see people from Europe who will be delivering talks along with the Europe and US and along with the Indian experts in the space science. So this is a very important program. I thank Dibendu for organizing this, and of course thank the ministry for supporting this program under this park. I see a lot of my friends who are here. Many of them, I'm sure, will throw light on this particular topic of machine learning in the space science techniques. As all of you know, the space science is a very important program of ISER Kolkata. I must say that. We have the Center for Excellence in Space Science Research under the SESI. It actually trains people to do analysis for space science, though our group is particularly good in the techniques of computational techniques and analysis of the space science. I think it is very important to complement with those who are actually collecting data, the experiments you are doing. And then the analysis really requires this knowledge of machine learning, will require the knowledge of machine learning as you go in future. So that is the objective of this workshop. And I hope this will be a very good training ground for the students. And I thank all the speakers who will be speaking, all the resource persons from India and abroad who will be participating in this. And of course, thank the student participants. They are very, very uh, uh, important members of this group because, in fact, their interactions are extremely important. So I will request them to interact very actively. Although this is being done online, today we are getting used to how to do things online. So, use the question answer chat box to interact with the resource persons. And I think with these few words, I see, of course, a lot of my friends. I don't want to name them now, but I see all of them here, and I welcome all of them to this particular workshop. And with this, I think I would like to inaugurate this workshop. With again, thanks to all of you, all the speakers, the ministry under the Spark program who are funding this, and of course my own colleagues in SESI, Dibendra Nandi and his team who are for organizing this particular workshop. Thank you very much.
Thank you, Professor Pal, for taking time out and inaugurating this workshop. Before we begin, we have some time, some 5 minutes. Let me just make a few remarks acknowledging the help of certain people who have put this together. Of course, this began as an initiative between India and Sweden, funded by the Ministry of Education under the Spark program. So I'd like to acknowledge the other members of the Scientific Organizing Committee, Axel Vandenberg from Stockholm University and Nordita, Dhrubaditya Mitra from Nordita, Choikot Chatterjee from KTH Royal Institute of Technology, Stockholm, and Shourangshu Bhattacharya from the Department of Computer Sciences at IIT Kharagpur. We have a very dedicated LOC run by our students. This is led by Shubhodip, who has done the bulk of the work. So I'd like to acknowledge the help rendered by Shubhodip Shina, Prosenjit Lahiri, our computer system administrator, Arnab Boshak, Chitradeep Shaha, Shomoranjan Das, Yoshita Borua, Om Gupta, Shobhik Roy, and Shakshi Gupta. So the proceedings for the next couple of days is primarily because of the big help rendered by this people that I just named. Let me also acknowledge, given that we have some time, the speakers who agreed to deliver lectures in this symposium. And as Professor Pal said, they're from all over the place. I mean, in no particular order, I'll just read out their names. So Shravan Hanasoge from TIFR, Ajit Kembavi from Ayuka, Shorangshu Bhattacharya from IIT Kharagpur, Vishal Upendran from Ayuka, Modhulika Go Thakurda from NASA Goddard Space Flight Center, Shoika Chatterjee from KTH Royal Institute of Technology, Sweden, Anubhav Ghosh from KTH Royal Institute of Technology, Sweden, Dipankar Banerjee from Aries, Lakshmi Beji from the Max Planck Institute, Pete Martins from Georgia State University, Shubhadeep Shina from IISER Kolkata, Shorangshu Bhattacharya from IIT Kharagpur, Srijan Bharati Das from Princeton University, Shubhama Chatterjee from the Southwest Research Institute, Arnav Ghosh from KTH, Stockholm, Paul Wright from Stanford University, and Shomitra Hajra from University of Massachusetts Lowell. So thank you very much for agreeing to lecture at this workshop. Remember that the morning lectures and the evening lectures are all going to be held online. The afternoon hands-on data training sessions are physical for those who are attending the workshop at IISER Kolkata, and it's online everywhere else for the registered participants. And the details of how to get involved in the online data analysis sessions for the remote participants will be given out at the beginning of today's afternoon session. So with that, I will welcome you all again to this workshop and invite Shravan Hanasoke of TIFR to deliver the first lecture. And before that, let me introduce to you Dhrubaditya Mitra, who is going to chair this session. So Dhrubaditya is from Stockholm University and Nordita, Sweden. He is part of the scientific organizing committee and was a co-I on this proposal. So Dhrubaditya, if you just take over from me at this juncture and initiate the proceedings, that'd be great.
Thanks, Dibyendu. So I am here at ISAR. Um, we are looking forward to 3 talks this morning, starting with Shravan. Hi, Shravan. Shravan, your mic is off.
Hi. Yes. Can
Hi.
you hear me? Yeah.
So why don't you share your screen and we can be right away.
Yes, done. So let me just do that. Can you see this? You can see the slideshow? It's a full slideshow?
Yes, we can.
You don't see the stuff above, right? Okay, yeah, it's just showing the slideshow. Okay, very good.
Okay, excellent. So
yeah.
Whoever has a question, please raise your hands when you have it. And Shravan, do you want questions in the middle of the talk or do you want them all at the end?
In the middle is fine. Thank you.
Okay, so we will go that way. And so whoever raises their hand, we will try to interrupt the speaker and try to see how it goes. There's quite a large number of people. So Shravan, all yours.
Thank you so much. And you'll give me a 5-minute warning. I mean, so when should I sort of start to wrap up? By about 11, 5 to 11?
I will give you a 5-minute warning.
Okay, all right, thank you. So thank you so much, Dibyendu and Dhrubaditya, for inviting me to this meeting. I'm sorry I couldn't be there in person, but it's exciting to speak to you. And I'm really looking forward to several of the lectures. They're super interesting. Many of my students are going to learn a great deal from this workshop. It's really quite timely. So, I just wanted to say it's not, these are not cliches. I mean, everyone will thank you, but I really do think this is very timely, and it's quite a nice thing that you've done. Okay, so let me begin. As you know, we started this whole machine learning program a few years ago in my group, and with time we've discovered that there's a great deal of really amazing things that you can do with it. There's a lot of pitfalls as well, and it's very challenging, but also profound if you can use it and if you're somewhat lucky. So let me describe some of the experiments that we've been thinking about, just 2 of them, and I'll describe to you some recent avenues, or I'll summarize with some recent avenues that we're taking at the moment. So as many of you know, the Solar Dynamics Observatory, among many other missions. I've just highlighted that here because a lot of our data analysis comes from SDO. Um, there's an enormous amount of data that it produces at a variety of different locations in the atmosphere and the photosphere and so on, different measurables and so on. And so we have an enormous amount of data, and it's not really possible for humans to go in and interpret what's going on everywhere in the data. And so machine learning then becomes really powerful as a mechanism by which to proceed. And so, the broad idea, which you'll learn, of course, in greater detail this week, with great specificity, is that you have some training data, labeled data, I mean, we're primarily focusing on what is known as supervised learning. And so there is unsupervised, and there are other categories of learning, that semi-supervised and so on, which are more challenging. But at the moment, because it's, we're not experts in machine learning, so we want to focus on a tractable problem. And there are plenty of labels already in the Sun for this type of data. So we take this large volume of training data, not large actually, it depends really on the problem at hand, but we take this volume of training data and we feed it into a machine, and we train it to connect it. We correlate all the training data with their labels, right? So for instance, is the active region flaring or is it not? Is this region of the Sun going to show emergence of a new magnetic field or not, and so on. So it could be binary classification, it could be regression. There are many types of problems that you can pose. And so then there's a whole group of unseen data, which is test data. So the machine should not have any inkling of what's contained in this test data. And so basically, you once the machine is trained, you say, okay, well, I'm going to feed in the test data, and I'm going to check that it's actually doing well. And so when the machine, or if the machine does well, so this process itself is very delicate and requires an enormous amount of effort. You have to make sure the data are very clean, etc., etc. Everyone knows junk in, junk out, so you have to be super careful. And once you've trained the data, then you can unpack the machine. Then you can start to understand what's going on with the machine, why has it learned what it's learned, and so on. And really, it's amazing what it can do, right? With conventional 20th century methods, you can sort of only go so far in terms of what you can do with these data. But machine learning can build high-dimensional boundaries between different classes in your data. It can learn very complicated probability distributions, and you can feed in very disparate types of data, like images, numbers, other types of labels, classification labels, and all of these together can combine in building this very complex model of the data. And so this is what we were attempting to do. Advanced machine learning techniques can reveal patterns in the high-dimensional space of magnetic fields, right? So we wanted to try to determine new things, and we were really hoping and exciting. We made some progress, not as much as we would have liked. So let me describe our success in these and failures in these experiments. So the first experiment that we decided was a very simple experiment, which is that in the Sun you have these sharps, which are basically, so you have these little bounding boxes. You have a little magnetic region, and not a little, it's a big magnetic region here, and you create a bounding box. And you say this bounding box basically highlights a region of magnetic field, and then you can do a simple analysis. You can create a vector of 25 or 30 parameters. So it's like the total unsigned magnetic flux, like the area of the active regions, some of the number of pixels, you have a current helicity, and so you have all of these parameters, right? These are vector magnetic parameters. And so you can combine the entire data, average it over the entire region, and you get all of these 25, 30 parameters for each, associated with each magnetic region as a function of time. So as this region progresses across the disk, you're tracking how these numbers are proceeding. So it's a slightly high-dimensional problem in some sense, right? So you have a 30-parameter vector as a function of time, and you want to try to build some type of boundaries within these data, right? In this high dimension. This is not really high dimensional, so it's embarrassing to call a 30-element vector high dimensional, but whatever. So it's you want to try to build a boundary there. And so that's what we use as a simple SVM, a support vector machine, which is super basic machine, but very simple to interpret compared to some of the more complex deep networks, which I'll also describe here. And what this does is, what this machine does is it builds a boundary, as I said, between, and we primarily look at what, we ask the question, in this, is this a flaring, is this region likely to flare or not? That's the simple question, right? So it's a simple yes/no classification. And the input is all of these sharp parameters, these 25 or 30 parameters. And then so this SVM, you train it with these binary classification labels, right? You say 1 if it's flaring and 0 if not. And so it's simple 2 numbers. It's not even a regression network. It's not giving you a probability. It's either saying it's 1 or 0. And somehow this is able to build a boundary between these samples. And so one of the problems with using these, with the flare problem, with the flare, if you look at flares, is that what we call flaring is M and X class flares, so high energetic flares, so it's a reasonable amount of X-ray flux coming out of it. You can always define it differently. Of course, there's a continuum in this flare density, right? So you can have lots of little tiny nano flares, but very few very large amplitude flares. And so there's a huge range of flares, and we focused on the high energetic end because that's in many ways the most interest and importance to space weather, right? So that's the end. So that automatically limited the amount of data that we had access to. And so there were only 85 samples. So sometimes a given active region can flare multiple times. And so, for instance, you only have 300. We had 308 non-flaring active regions, and 304 M flares, not active regions but flares. Right. There's only 85 flaring active regions, but you get 304 M class flares and 24 X class flares. So a single active region will flare, not will flare, but will most likely flare multiple times over its lifetime. And sometimes it does low amplitude flares, and sometimes it gives you an M, and it very rarely gives you an X. And so you can see the statistics are declining very sharply as you go to the high end of the amplitude. And so then we do what is known as a tenfold cross validation. So you slice and dice the data in different ways. So like you define a training data set, you define a validation. That's all part of the training, and you define tests, right? And so there's a partition of your data, and you can do the partition randomly in different ways. But there's one holy rule, and the sacrosanct rule, which is the machine cannot see the same active region, that you cannot mix the measurements from a given active region in the training and the test data. So when you have an AR label, an active region label, like a 12599 or something, that can either solely belong to the test data or the training / validation data. You can't mix the two, because then you get erroneously high success rates, right? So we've seen in the literature that people sometimes mix these active region samples. And the thing is, machines are always looking for tiny biases, right? They're looking for you're trying to get a machine to detect something that's really faint. And so if you feed it multiple samples, different samples from the same active region in the training and the test, it recognizes this thing, and because it's looking for the smallest biases. And so you lose accuracy there, or rather you're inflating the accuracy, right? Your machine seems to perform really well and you get super high success rates, but it's not a real thing. So when you don't mix them, you don't get very high success rates. And when you do mix them, you do get high success rates, but those are misleading success rates. Okay, so that's the general setup. And what we do is, and so here's the first insight that we developed, right? So we said, okay, let's look at something like instantaneous recall, which is the number of true positives. A true positive is, so the whole problem setup is a statistical problem. What we're looking at is an ensemble. So we're looking at what's happening to all of these 304 M class flares, what's happening to all of these 24 X class flares, and so on, right? We're not looking at flare by flare. The signal to noise associated with measurements of any one given flare event is simply too low to draw broader conclusions. So we do a statistical average over this entire sample. And so what we do is we ask, what is the machine saying, right? I told you the machine can give you either 1 or 0. And so 1 is what is called a true positive, and 0 is called a false negative. Okay, I mean, if the machine successfully, so the true is a prediction of the machine, true or false, like 1 or 0. and P or N represents the ground truth. So P is positive and N is negative, right? So P, that means that if the machine said something was flaring and it was truly flaring, it would be a true positive. And if the machine said that something was false, i.e. 0, and then the flare, and there was no flare, the active region was not flaring, then it would be a negative, right? So this is what we define as the instantaneous recall. It largely tells you, for this statistical population of flaring regions, how accurate are its predictions, right? How likely will it tell you that something is flaring or not? And so this is a very unusual measurement. So this was a paper some years ago that we wrote. And we found immediately that, that if you looked at this instantaneous recall, which is the likelihood or the accuracy of this machine telling you that something is flaring or not. So this 0 is on the x-axis is flare time, and then this is the identification rate, right? Or this is the instantaneous recall. And it's telling you 0 is the flare time. It's telling you for days prior, the machine is able to tell that something is likely to flare. These are the error bars, the shaded gray, and the black line is the ensemble average over the entire population of flaring regions. And it's telling you that basically some class of flares, or some class of active regions are just have a greater propensity, right? Their parameters that define that system are basically almost always in a state that's called flare productive, which means they can flare at almost any time. So, very, very long before the first flare is recorded, it's a little bit low, but as you get closer to flare time, we align all of the data, right? So we have 85 different active regions and we align everything. There are lots of subtleties also there, which I don't have time to get into, but we align everything so that the flare time actually is at 0. And so you can see that basically the machine is able to detect that some active regions have a greater propensity to flare than others with very high accuracy, right? So these are small error bars basically. And so what's happening? What is the machine actually detecting, right? So here's a dynamic view of, remember we're only feeding the sharps into those vector of 25 parameters. So with these are actually magnetograms that are telling you what's going on. So AIA is going to tell you when something flares. And so this is the machine identification. This is the magnetogram here. I'll play this again. And this is sort of the emission, right, from this region. And every time it's bright, basically it's like a little bright thing, then it's a flare. Or you can look at these black vertical lines. Those demarcate the flare times, right? That's when an M or X class flare has happened. And you see the magnetic region here. Okay, so you have some small changes, and there's a little bit of flux, mixed polarity flux that's showing up here. And so the machine sees it and thinks, okay, well, maybe something sort of happened. And then a lot more flux starts to appear and the machine trips into a positive mode. It says, okay, now new mixed polarity flux has occurred, and then this machine is basically predicting that this active region is likely to flare. So indeed, over this time, over this period where the magnetic region or the active region flares, you see the machine is correctly identifying it, but you also see what's going on in the magnetogram, right? And remember, we didn't train it with the magnetogram, we just trained it with the sharps. So you can see that there's basically some change in the unsigned flux of this entire region. And so flare, machine is also saying, red means the machine says 1, and blue means the machine says 0. So you can see that the machine has recognized that this type of event is basically a precursor to a flare. I mean, this is a vague thing, it's not that precise. But it's telling you that the occurrence of new mixed polarity flux is a potential leading cause for flares. Okay, so now we look at what we have about 100 flares, and we're asking what is going on with the parameters, right? Like the sharps. So we say this is the unsigned flux basically, and this is a flaring region, and this is a non-flaring. This is a typical non-flaring region, a false negative. You can see basically, this is of course really well known that flaring is highly correlated with the extent of the magnetic field strength, right, or the magnetic field amplitude. So when you have a high magnetic US flux, unsigned flux, then the machine immediately says, okay, well, this is likely to flare, right? So there's already a strong correlation with this extensive property. But then there's something very interesting again that we recognized and had not been seen before. When you average this population of flares, you find that there's a net current helicity, which is ABS and JZH, which is, and in fact, one of the most critical parameters that identifies flaring, or highly correlated with flaring, strong flares. This is sharply increasing with proximity to the flare time, right? So at time t equal to 0, the net current helicity reaches a peak and then appears to dissipate. It's not symmetric, so it's dissipating more slowly than the buildup. So you can see that there's some, but the error bars are tiny, and this is what, like a false negative, which is the typical active region's doing, right? This is the level that it's at. So there is something. First of all, the amplitude of this signal is much higher, and then secondly, there's a time variability that you wouldn't have seen in a single instance. You typically need to average a population of these to measure this. So there's another new insight that the machine has basically told us. And so, if you have we tracked about 20, we hunted for these new emergences, active region emergences, and the ones that actually ended up flaring. And we see that basically the error bars are larger here because we don't have as many instances, but we see basically it's rising smoothly, right? So when it goes to flare time, it's a smooth rise from emergence all the way to flaring. So these are not even that many samples, but you see a very clear signal here and fairly small error bars. And yeah, so there are other parameters that we look at. That's fine. I don't want to draw your attention. So these other ones, nothing much is particularly happening here. The area, the mean free energy, and the R values, nothing is particularly, they show some interesting trends. But anyway, so I didn't think that there's anything particularly fascinating there. So then what we said is, can we train this on the magnetograms itself, right? So there's a lot more information in the line of sight magnetograms, and they contain spatial information. They encode spatial information basically. And we said, what if you take this 2D image and you fed the 2D image instead of these vector of 30 parameters, right? And what we had hoped is that the machine would identify features in this magnetic field that were highly correlated with flaring activity. And so then we used this convolution deep network, multi-layer deep network, and there's multiple layers here. There's max pooling, and they're a fairly complicated network. And then the output is basically classification, a 1 or a 0. But in this case, it'll be a regression. So it can be a number, a real number between 0 and 1. And what we found was that, we were hoping for something more dramatic, but we did not succeed, unfortunately. There's a lot of biases when you're given images. The machine tends to focus on all sorts of junk. And this is a well-known issue with machines. It's very difficult to try to get them to focus on the sorts of things that are interesting to physicists, right? It'll do something that's, what its job is to classify, and it'll use anything to classify. So if your images, for instance, if your magnetic field images are slightly blurry for some of the false negatives or slightly blurry for the flaring active regions, it'll immediately associate the blurring with flaring, the inclination to flare, right? So it's using literally anything it can to do this classification. So that in itself also presented a lot of challenges. In fact, when we trained the machine on these images, there's a lot of work that that we had to do in pre-processing and et cetera, and the sizes of these maps, right? The magnetograms, they're not uniform. So if you try to make them uniform, and then you reduce the resolution on some or increase the resolution on other, or you try to use a nonlinear compression type thing, then that'll use that as well as some type of way to discriminate between these. So we worked quite a bit on the machine actually. And so now, and ultimately we fed in all of these images in their natural original size. And so the machine could take images of different sizes. But in the end, unfortunately, after a great deal of effort, all we were able to determine was that the machine is sensitive to the polarity inversion line. There's no great discovery there. This is what is known as a gradient map, or a saliency map. It's telling you what the machine is paying attention to. So this red marked region here is telling you what the machine is paying attention to. And here is the identification rate that I said earlier, right? So these are different. We compared the predictability, the quality of prediction with the line of sight magnetograms with the previous ones, with the sharps. So you don't get any great improvement. So the images are not telling you anything new. It's just those average features that we get. The vector of 30 is as good as this entire image, at least with the machine that we used and the type of data analysis that we did, which was, I think, quite disappointing, because we were really hoping that we could improve the level of the quality of predictions and so on. Anyway, the saliency map basically indicates that the machine is looking at this region. Again, there's not a great deal of like exciting insight here, but some insight, I suppose. And then we do other and these are the types of biases, right? That I said was very unfortunate. We find that it depends on the resolution of the magnetograms. So sometimes when you're downloading HMI magnetograms, depending on the angle that you're looking at, looking at the field at, the resolution is not so good. It's a little blurry sometimes. And so when you look at these images and you look at the resolution also, you find that there's some sensitivity. The machine is trying to use, as I said, it's using anything it can to make this distinction, this classification. So unfortunately, we found that it was also sensitive. The classification output was sensitive. And we did all of these different tests. We said, what if we put a bipole of this size? Would it, with a certain resolution, would it try to detect it? What type of synthetics can we feed into this machine to trip it into a positive or a negative state, right? So you can do all these engineering experiments where you design some synthetics and you feed that into the machine, and you ask the machine to say, is this going to flare or not? We didn't find anything exciting, very unfortunately. We found some ratio, like of the most likely ratio of this thing to explode, for the machine to predict something was going to flare or not flare. And ultimately, it depends on on the image quality and things like that. So that was a bit of a bust, unfortunately. So there are some lessons. We were able to say, as I said, for days before and after the flare, the flaring active region is flare productive. So it's in a state where it's in a critical state. It's likely to flare. It can flare at any point. And ultimately, unfortunately, the machine is looking at a few quite boring things, right? It's looking at the size of the magnetic flux and things like that. So the accuracy is not as exciting as we had hoped, but but we learned something about the electric current, the net ABS NJZH, which rises sharply and dissipates after. So and then ultimately, when you do feed it images, you have to be extremely careful when you feed it images, and the machine is using all sorts of biases to make this separation. So there are positives, and so we did try this variable size magnetograms, and that also didn't produce anything dramatic. Okay, so I'm going to switch gears and talk a little bit about flux emergence, which is a very it's a bit of a holy grail in solar physics. Can you predict any of these things? Sorry, just a second. Can we predict when a new magnetic field is going to arise? And it's a very challenging problem. It's what is known as all of these problems typically are class imbalance problems, which is that the overwhelming fraction of the various parts of the sun will show no new flux emergence. Okay, you have to define what flux emergence means. But if you say flux emergence corresponds to an event where you have a sufficiently large magnetic field that comes, that rises up to the surface, right? If some critical threshold, but those events are rare. So if you looked at any given patch of the sun, you will find that there'd be no new field. So if you trained the machine on this, and the machine just kept saying no all the time, you'd be right like some overwhelming fraction of the time, right? So your machine is sort of quote unquote accurate all the time, but it's not really what we're interested in. What we're interested in those edge cases, right? So can you say something about this? And one of the issues is that this signal to noise of these emergence events, pre-emergence events, is very low. And so I won't describe that particular direction, but we've discovered some very exciting possibilities for denoising solar data to try to detect hints of emergence. And we have actually made quite a bit of progress in this direction. But that's ongoing work, so I won't really describe that particular result. What I'm going to describe to you is work that we've already done on flux emergence. And so what is flux emergence really? So you have, this is the peak flux in some sense, and and then you say that this is some 36 hours prior to what you call when the flux has emerged, is when the emergence event starts, okay, or I think it's T0, 10% of it or something, okay, and there's some definition for when emergence has begun, right? So, and this is the emergence time. Flux gradually emerges over the next 36 hours, and so what we do is we take these magnetograms. These are data that Aaron Birch and the colleagues at MPS had already put together. The very nice data set of clean emergences. So, flux emergence where there's no large magnetic flux already prevalent, and there's a sort of a quiet sun region around it, and so on. And so you can basically take these 7-hour averages over the magnetograms, nanosite magnetograms, and those are pre-emergence. And you can similarly take averages of non-emergence magnetograms. So of which, as I said, there's some infinite number. So you have as many control samples as you want, and only very few it's like 180 or something instances of clean emergence. So really not that many. So these are small number statistics, and so we had to do a lot of tricks to try to train a machine on this. And so what we did was we have these pre-emergence magnetograms, and these are control regions. You can see some stuff happening here. That's at the central region. So some sort of dipole is showing up, and so you can see the it's marked here. But in a non-emergence map, you don't see anything at all. So this is just pure noise here, and this is an emergence event. So you see something going on there. And if you average all, this is in one given AR, right? So this is 12089. So the signal to noise, as you can see, is really quite low. But if you average all of the 180 or so that we have, then you see a very clear bipole here. So sorry, you see a clean bipole event that comes, like nearly 10 hours prior, 19 hours prior. Sorry, you can start to see this event, and so there is definitely some signal there.
Raman, this is Dibyendu. Quick question. So this is purely magnetogram images, right?
Yes, these are magnetograms. Yeah.
Okay. All right.
Yeah. So then what we do is now we're stuck with, as I said, 180. So there's not a whole lot you can do. So yeah, you have 178 only. This is it, right? So I mean, okay, like at different times you have different numbers of them, because sometimes the whole analysis happened within 45 degrees of the central meridian. So this 20, like at minus 24 hours, sometimes these are outside of those windows basically, and so you have fewer maps. Anyway, so this is the maximum number, 178. So as I said, 180. That's all. So these are very small numbers of things to train a machine at, and even do more complex analysis, right? So how do we increase the amount of data? So what we did was we took these are 30 by 30 degree maps, and we split it into randomly selected 10 degree by 10 degree tiles, which are 85 by 85 pixels. And the whole image 30 degrees was 256 by 256. Okay, so these are smaller images, and if this box contained the emergence event, then we would label it a 1, and if the box did not, then we would label it a 0. So it could even it would have to contain some fraction. I forget now what exact discrimination we had, but if it did not contain some fraction of that emergence event, then
there is a question.
Yeah.
Could the person ask the question, please?
Yeah, please, go.
Okay, so let me say that. Does the error is from Ashwin Amrita Raj? Can the errors be reduced if we use other wavelengths to detect flare emergence instead of magnetogram images?
Yeah, so that was something that we tried actually also. We didn't get very far, but there's some hope for using all these atmospheric data also to train it. It's a big pain because you can do it. It's a big pain only because it's like a data analysis exercise, right? So it's the same thing, like you got to cut all of these. Unfortunately, the AIA data and so on, I think, are more challenging to deal with because they're not already necessarily been prepared for these flaring regions. We started with the sharps because they were already present and it was easy to get the magnetograms. But yes, the answer is yes. We just hadn't done it. There may be some hope for improving signal to noise, but there actually may be hope for denoising the data itself. So I'll describe a little bit about that at the very end. There's no slides per se, but I'll just talk about it. Are there other questions?
No, that's all at the moment.
Okay, all right. So anyway, that's how we sort of split up the data, and then you take the non-emergence regions. They're also zero, most of them. So one thing I'd like to point out is there are always flux emergence events, right, of various magnitudes. So there's tiny flux tubes that are coming up and disappearing, and so on. So like even this, I'm sure, like some of these flux emergence events could be this one maybe. So it's really a question of what you define as a flux emergence event, right? So that's up to you. And we, as I said, defined it based on a critical threshold of magnetic flux, right? When it starts to again become relevant to space weather. So these tiny flux tubes are, generally very unlikely to create flare events and so on. It's only the bigger sunspots that are highly correlated with flare activity. So that's the reason why we didn't. That's the reason we called it zero. So this we term as background noise. There's a lot of noise, and then there's a weak signal here sometimes. Right? And so again, now we go into a deep network, and this is a classical, deep CNN, and we train it, and there's an output that gives you, it's a regression network, and it gives you a number which tells you what is the likelihood of this particular magnetic map to contain an emerging magnetic region, right? And this is what a CNN does. It's kind of like a wavelet transform. It takes it's a sliding wavelet of different sizes, and it takes various averages, and so it deconstructs this field into all of these multi-scale features, and then you get a sequence of feature maps depending on the size of this box, and each map is the translation of this unit box across it, right? So you see that this is moving around. So it reduces. It's some sort of average in this region and reduces it to a point, to a number. So that's what a CNN is doing. It's decimating these images into different sizes, and then you get a sequence of maps like this. Okay, and so then you define some entropy function as your penalty, and you proceed to do the to do this training. So okay, so the training is finished, and it was doing remarkably well, and so we defined, or very well rather. So we defined we defined this true skill statistics, right? And so these guys are using, Barnes et al. Are using discriminant analysis here, and this is just using the total unsigned flux, which is a simple discriminant analysis actually. This is one type of discriminant analysis. This is another type of discriminant analysis that use just the total unsigned flux. You're already doing pretty well if you just use the total amount of unsigned flux in that region. But the CNN does outperform above the error bars, all of these. So then we got excited.
One more question from Devesh Bhattacharjee.
Yeah.
I want to ask how much of the classification results are sensitive to the signal to noise ratio of the magnetogram data?
I mean, they are very sensitive. I mean, as I said, the machine is trying to do everything in its power to discriminate between flaring and emerging and non-emerging regions, right? So if there's a bias that some of your emerging regions have a slightly lower resolution, or like they're a little blurry or something, the machine will use that as a way to discriminate between these. It's not a smart machine, right? So it's only as smart as the data that you give it, and so you have to be very, very careful, as I said. I'm sorry to emphasize that again and again, but yes, the machine is sensitive to all of these features, and you have to be quite careful. Yeah. And so, okay, so we find that this is, performing, and so we got excited because we said, oh, well, the machine's working better than, better than this other thing. So maybe the machine's actually understood something or detected some features in these data. And so the first thing we found was that, I mean, this discriminant analysis is building like a very sensitive boundary, right? So it's basically saying that when you have an intermediate amount of unsigned flux, that's when something is classified as a pre-emergence. P is pre-emergence and ME is non-emerging. And then if it's below some threshold, then you're saying that it's no. So that's what this MTOT discriminant analysis thing is doing. It's building like a very sensitive boundary. Now we try to investigate what the CNN is doing. Right? The CNN is also building a complicated boundary. And so then we tried a number of tests. We said, what is the mean CNN output? Which is that I told you this is the output, right? This number, 0 and 1. So what is that output as a function of total unsigned flux? And we find, yes, that it's also sort of like doing this thing, right? It's peaked at some intermediate value of the unsigned flux, but sort of falls. So it's basically saying from the data that it's seen, which is a very limited sample, that it's and there's some. This is the most likely. As I said, it's not clear whether there's any physics in this, right? It's just building a boundary and it's seeing the data and it's saying that this is associated US flux with emergence, right? So this is the type of caution that you need to exercise when interpreting this. And then we tried to do machine interpretation, and so this is one of these cutting edge areas in machine learning as well. And so we worked a lot on this machine interpretation, and we studied all of its filters, and we said, okay, what is the filter output? So there are these multiple. So every CNN outputs all these filters that are processing the image, and we looked at these filters, and they have some unknown weights and so on. We said, what happens when you feed in this magnetogram as it processes it, as the machine processes it through the network? We stopped it at every stage and we looked at the filters, right? And anyway, so it's very complicated to try to immediately understand. But the machine, what this says is the machine is seeing that there's a magnetic flux region and paying attention to it. So it sees that there's a thing.
You have about 5 minutes.
All right, thank you. So anyway, so that's what the filters are doing. We studied those, and okay, but you already saw this thing. So and then we tried these experiments where we said, let's put a synthetic dipole, and then can we see what happens when you change the shape of this dipole and the amplitude and and so on. And we found that nothing particularly gripping, right? So we didn't find anything truly fascinating. So the machine has learned something, but exactly what it's done is not fully clear. So can we say that we forecast emergence, and we didn't really try that problem? Although I'm starting to think that maybe we can with this denoising effort, which I'll describe in a second. And then did we train this CNN? Yeah, the training was superb, and it just did very well in comparison to discriminant analysis and so on. And yeah, so this is what it suggests, that small scale and intense fields produce high CNN output. But how robust this measurement is to increasing the data set and the variability of the sample is not, the variance of the sample is not fully clear. Okay, and so a lot of effort in trying to interpret it, but that did not was not very successful. Okay, so I'd say that it's yielded some results, the machine learning applicated work, but it's limited because in terms of physical insights, we, for the problems of flares and the problem of emergence, we just don't have enough data. And so there's not, I think that's one of the significant problems in this. And so we've just not been able to push it as far as we hoped. But what's very, very interesting is, and I'll describe this in words, my student Prasad Mani has been working on flows associated with the active regions, the pre-emergence active regions. And we find, I don't want to describe how we trained the machine, but that machine is going gangbuster. I don't know how the machine's doing so well, but it's doing extraordinarily well. It's able to denoise the data to some extreme levels. So it's able to, detect features that are, at signal to noise of 1/5, 1/6. We're not quite sure how it's doing it. But we have ground truth. I told you we have actually it's only 108 samples of these flows that we have. So it turns out that only 53 of these 108 emergences, clean emergences, produce associated flows. So the 55 of them have no flows at all. So some of this magnetic flux seems to be rising to the surface with creating zero disruption, right? There's no flows, there's nothing. It's very, very, very weak flows. And only 53 of them have these associated flows, right? So it seems to suggest that this canonical picture that we have of a flux tube that's rising and creating this little, movement of fluid around it is actually not so robust. It's only some small fraction of them that's doing, or rather some fraction of them that's doing this. And there's an equally large fraction that's just coming up with zero noise or zero flows, right? So this leads to some super interesting questions like, are there different formation mechanisms? So we studied what happens to these magnetic fields, right, as they evolve. What happens? We tracked the sharps, or the 53. That we found 53 active regions had flows and 55 had no flows, associated flows. And we tried to understand what was going on with the 55. How was it able to rise to the surface, and does it mean different? What implications does it have for the eventual magnetic field morphology and the flare productivity and so on? So we haven't been able to find any significant statistical differences in the eventual magnetic fields themselves. But it leads to super interesting questions, right? Are there different formation mechanisms for these? Why are some fields of comparable magnitude, coming up to the surface with, significant flows on the order of 80 meters per second, disruption of flows, and some are just coming with zero flow amplitude. I mean, we're seeing very little flow amplitude. So anyway, we're sort of focusing on that, and we're thinking that machine learning can denoise as a denoising agent. It's a lot more powerful than some of the stuff that we've done before. So that's where we're putting a lot of energy in right now. So with that, I'd like to conclude, and thank you very much.
Thanks, Shravan, for the great talk. We have some overlaps, but I will hold those questions now, and we still have a few minutes for questions. So Dibendu has a question. Dibendu, go ahead.
Yeah, Shravan, thank you for that nice overview. Question for you is, based on your experience, you've used both parametric techniques for figuring out the difference between fair productive and non-fair productive active regions. You've also used images. Do you believe that going towards images is something that that is meaningful in terms of the much higher processing power and time that is required, or you think the true skill scores that are being achieved now, which are very high based on parametric rankings themselves, are sufficient?
I think we haven't seen any additional benefit. You saw that. You saw this thing, right? So let me just show that one slide here. You saw that. Sorry, 1 second. There's no improvement whatsoever in using images. And we were hoping for physics. We weren't hoping for improvement necessarily in predictability. But look at this. This is line of sight. This is that instantaneous recall, right? Like what is the likelihood of this active region to flare? 0 is flare time, and then this is pre-flare and post-flare. And you can see that they're all identical basically within error bars. The error bars are larger than this for sure. And so you're seeing that line of sight, is no better or worse than these other methods in these parameters, right? So, I mean, I don't know. I think they're too noisy basically to be productive. So the answer is no. I don't think they're useful.
Thanks.
Okay, the last one. The administrator, can you please give speaking permission to Hemapriya R? Meanwhile, while that is being done, there is another question from Ashwin Amrita Raj. Is the position and polarity of the spots have any relation with the flow of the flux? The zero flow of the flux seems so interesting.
Yeah, I mean, the position, I don't know what the position, polarity, you mean, in the disk, on the disk, is that? Yeah, I mean, we don't think that there's any correlation with that. There should be. They're all very clean emergences. So they're within 40 degrees of the central meridian. So they're not like at some weird angle and so on. They're not necessarily at high latitudes. They're at sufficiently low latitude and so on. And we haven't seen any particular preference, and we don't know why some of them are coming with no associated flow. So
the last one, Hemapriya, I can't seem to give you.
Hello.
Go ahead.
Yes. Thank you, Dr. Shravan, for a wonderful presentation. So I have a question. So when we see in Bogra et al. Paper about the prediction of flares with CMEs, so we see that the model performance is better in the time of pre-flare of 24 to 36 hours, while the model performance is lower when we near the event occurrence, like 8 or 4 hours. So do you think any, because we expect that the model should be performing better when nearing the event occurrence. So do you think there is a rapid change in the process during this hour?
not that we were able to detect. So we did a statistical average.
Okay.
So this is over the 85 active regions and the 300, and so flares that we detected. So you can see that it's basically stable over the. So the prediction rate is not changing very much
Yes.
as you approach zero flare time. So yeah, that's what we would expect. We would expect that you get into the state, or maybe there's a slight rise, but you're seeing a slight decrease, is it?
Not here, but in the Bobrolitol's work.
Oh,
So that was when we were trying also, we were facing the similar condition. So we were, because I am a bit non-physicist in this area, so I was very surprised to see that, and I wanted to know, is there any rapid change in the process before the event occurs?
hmm. Hmm. So not that we were. Yeah, I mean, this statistically, I showed you this thing, right?
Yes, yes.
Uh,
Here I can see it is not changing
yeah,
much.
this one, right? It's rising rapidly.
Yes.
This is the only parameter. Yeah.
Okay. Yeah, thank you.
There's one more question. We have time, Drupaditya, or?
Yeah, one more question from Shubhadeep. We can take that.
Yeah, thank you.
We
So,
have 1 minute.
hi Shravan, this is a nice talk.
Thank
And so I have one question regarding the flux emergence part.
What are the for the data gathering? What are the options available in India right now? So we have got two really beautiful observatories working, absolutely world-class results. One is AstroSat, launched in 2015, expected life 5 years, but going pretty strong even now. And then there is the GMRT with its many antennae and with which astronomers from all over the world are getting massive amounts of data. It has got a upgraded version now, which is 10 times more sensitive generally. Okay, then you have then in next year. I mean, 3 days ago I was told that January 1, no, January is the expected launch time for Aditya L1, which will be a great event for all of you solar astronomers. Okay, and then over the coming decade, it's going to be the TFT, which was supposed to be decade, but which has got horribly delayed now for non-technical reasons. Then you have got the LIGO. The LIGO machines abroad are going very well. Right now they are being refurbished, but we expect fabulous results again quite soon. And then the Indian LIGO has been nearly approved, but not fully approved yet. We are waiting for that. Then there's a square kilometer array in which NCRA and RRI and others are playing major roles. And then we'll have the LSST. I always forget what is the new form for LSST. The old days it used to be called the Large Synoptic Survey Telescope. Now it's a Vera Rubin Observatory, and LSST has got different uh, words attached to it. So then what do we do with all this data? We have to find patterns, correlations, classes, outliers, and meaning in the data. And whatever Shravan Hansoge said a moment ago, that was an excellent example of looking at solar data and trying to get new patterns and new meaning in it using machine learning. So in general, we need data analytics, which requires domain knowledge, requires a lot of mathematics and a lot of statistics. Okay, so so therefore, in astronomy we are very comfortable because our domain knowledge itself requires mathematics and statistics. But that is not true with the other domains. And then we have got visualization, data mining, and then of course uh, we apply machine learning and deep learning. Deep learning is the going thing now, very important. So I remember that at the beginning of the talk, Shravan summarized what machine learning does, but this is a repeat of that in a slightly different form. So we have got a lot of data with us, and then we pass it to a learning algorithm, okay, to get a trained model from it. Right, so this is a training data. Now, once you have got a trained model, it doesn't matter which machine learning or technique that you use, but this is the general path that you follow. Once you have got the trained model, then you use test data to assess the accuracy of that you have reached in the process, and what the recall, meaning how many objects that you want to detect are really being detected. Right. So then we could of course you could then you use it on unknown objects. Now here, in the input data itself, you could have data with labels, which is supervised learning, right? So because for example, because there's a galaxy, there's a star, there's a star. That's supervised learning. Or we could have data without labels, and you a machine learning algorithm do all the work for you. Okay, so then now what's the difference between machine learning and deep learning really is that in machine learning, you use extracted features from the data. Okay, meaning that you have to engineer the data to find useful features from it, and then you pass them to a machine. Whereas in deep learning, you just check the original data to the system. Okay, and then it does what it requires to do. So now, let's take the bull by the horns and look at a typical multi-layer artificial neural networks. So what you have there here is that you have got an input neurons, okay, where you will input your information and extracted information about your data, and then you have got the hidden layers, which basically do the classification, help in the classification, and then you have got output layers. And you'll see that in this particular version, so every neuron in a later layer is connected to every neuron in the earlier layers. Okay, and so these are called, so this is called a fully connected network. And then, so what do you want to do with this kind of a network? You can see that here is that let us suppose, now this is a two-dimensional space here, x1 and x2, and there are two kinds of points here, and the red and the blue. The colors are not meaningful here. It is just that the coordinates are the input. And what I want to do is to try to train a machine learning system, right? So that if I take a new point and give x1 and x2, then I'll say, then it will tell me which group it belongs to. And then here you have got 5 input nodes, and so therefore you will be talking about a 5-dimensional abstract space, x1, x2, x3, x4, and x5. Right, and then so there, now if you have got 2 groups, there will be only 2 nodes. If you have got 4 groups, there will be 4 output nodes, and so forth. Right, so this is what you want to do. And then there's just a very quick thing. I don't have enough time to go into this now. Is that you see that you've got the input nodes, and then whatever you input, that is added together using the weights here. So you can say the vector z is equal to w times the vector x, and w I call the weight, and then you pass it through a non-linear function. So which could be, for example, a sigmoid or a ReLU function. And then you output these to the next layer, and there again you have got same your z with new weights coming in, and then you have got the output function, non-linear function, and go on doing that until you reach the end. Right, and so there you will get your outputs. Now the idea is the following: is that if you look at the points which I showed you, then the idea is that you put in the points and you say which class do they belong to, the points, the red class or the blue class. Right, so you just put in one set of coordinates, and then you get some output here, and then you put the other one, like that. You'll get different outputs. And now what you want to do is that you want to alter the weights so that the output is what you want. Okay, so therefore you have got the training output, you have got the observer output, you've got the true values that you want, and you set up a sum of least squares over all the things here, and you get an error function. And now what you want to do, like in all error function, is to minimize the error function, and which will give certain level of classification. And the minimization itself is done by using something which is called back propagation. So when you alter your weights on this side and gradually propagate that to the beginning side, and then when you do that, then you see you have classified your points. Okay, meaning that your machine has learned to distinguish between these two sets of points. If you now give me coordinates x1 and x2, I can pass them through the machine and tell you which class it belongs to. And then you see this is the surface here which divides the two. But I neither started with an assumed surface and then I got the best surface. nor does the best surface any have a specific meaning. You can just say that this is a surface which gives the best partition between the points. The thing is that I did not ask the machine, I did not give any starting things to the machine. The only thing that I given to it is the data. Now, when you go to deep learning, you you see that you don't have the extracted data. You put in your like for example, if I want to do an image, classify an image, as I'll come to, okay, then you see that I don't break down the image into its engineered properties, okay, and then pass them to the machine learning system. That is done at the ANN level. At the deep learning level, is completely different. So here, for example, so we want to classify, we got pictures of dogs and cats, and then we want to classify them. So you've got the different layers of classification. I'll come to that in a moment. And when you train the system, but the problem is that you've got a standing dog here, there could be a sitting dog, there could be different breeds of dogs, similarly different breeds of cats, and then there could be different situations, they could have different backgrounds. So all of that has got to be taken into account in the learning. So what you do is that you take images of these things, typically three colored images, and then pass them. And what each one of these units does is that it breaks up the image by applying convolution, by convolving the image with a set of filters, which examines the edges between them, examines the curves between them, the textures of the image, and the overall appearance and so forth. And it keeps downsizing the data at each stage until it comes to a point at which you can use a fully connected ANN to classify it. Right? So therefore, so you see that it is very profound really. You are breaking up an image into parts which are much easier for the brain to discern. I mean, that is exactly how we see it. If I look at Dibyendu's face, I'm not going to analyze it pixel by pixel. What I do is that I say, I know this guy, I know his feature, that is Dibyendu. Okay, so so that is the way it goes in this technology. So here, for example, you've got a trade system which can distinguish between a car, a truck, airplane, a ship, and a horse. And then you see that when it's presented with this image, the length of the bar gives you the probability of it being a car. And you see clearly you can very well classify this as a car. But then, of course, you have to give the accuracy. Okay, meaning that in what percentage of cases do I correctly identify a car? And then you need good recall. Meaning that if you give me a sample in which there are 100 cars or 1,000 cars, what fraction of them can I correctly identify? And so you got a CNN architecture. Okay, then you have got all these are called convolution layers, and these are called the pooling layers, which downsize the data. And then you come finally to the layer where the classification is done. Okay, so now what I'm going to do is stop talking to you about these networks in the abstract and then apply and then give you just two examples where you can see this CNN and machine learning in action. So at this point, does anybody have a question? No,
Not
then
at
I
this
don't.
stage. Please go ahead.
Yeah, all right. Okay, so so now I come to bar detection in galaxies, and uh, I suppose most of you are familiar with solar astronomy, but some of you should be also general astronomy. So where we have, so if you look at these three galaxies, and then you see that each one of them, and these two are spiral galaxies. This is what is known as a lenticular galaxy. A spiral galaxy has got a bulge, a disk, and the spiral arms. A lenticular galaxy has got the bulge and the disk, but no arms. And in every case, you see this linear structure there, which is known as a bar. The bars are present in about maybe 40%, maybe 50% of galaxies. These are extremely important structures. They arise dynamically within the galaxies, but they could also arise through interactions with other galaxies. What the bars do is that they help to channel gas and stars from the outside to the inside. So, which means that they trigger evolution of the galaxy. They're very important. And our question is, what fraction of the galaxies are bars? And what are the circumstances in which bars occur in a galaxy, and so forth, and which requires you to produce large atlases of bars. So here's a beautiful galaxy, M51, full face-on view, and then you'll see that there's no bar in it. So there are a majority of the galaxies, of course, are unbarred. Okay, so now what we want to do is to take a large set of, these are all unbarred galaxies, these are all barred galaxies. In some cases you can see the bar very easily, in other cases you don't. And we take very large sample of this, and the idea is to train a convolutional neural network to be able to say when a bar is present and absent. So there are two postdocs, Shilu Abraham and Arun Anian, who did this, and my long-term AI collaborator Sajid Philip and I were there on it. And then you see that now why do we choose 12 layers? So why do we choose a machine learning network with two hidden layers? In the case of machine learning network, it's very easy. Because as you go on increasing the number of inputs, and if you go on increasing the number of layers, the number of weights becomes unmanageably large, and you can't go beyond a certain point. Okay, so in the case of convolutional neural networks, whether you want how many layers you want to use and so forth, that is partly art, partly science. It depends entirely on your experience. And the idea would be do the least that you need to do to get the result that you want. Okay, so so now we had a training sample of 2700 barred galaxies and 2741 unbarred galaxies. Now, as I told you, the SDSS have got several hundred million galaxies in it. And then now you might imagine that I know all of them which are barred and unbarred. So why these 2700? The idea is that it is incredibly difficult to get training samples for deep learning. Now you may think that it's true only in astronomy, but it is true in absolutely every field. Getting large training samples and very large training samples are required is extremely difficult. And so here you see that you have to take whatever you got, and then you need to augment your sample and so forth. And so here you see that these two galaxies have been passed through the convolutional neural network with these convolutional filters. And I'm just showing you as an example. So the kind of features which are extracted from this one. And so and these are the kind of features on the basis of which the classification is going to be made. And you see here, so the barred and unbarred, the true labels, and these are the labels which the machine has put. And then you see that you've got large numbers along the diagonal, which means that the classification is highly successful. So if you define these parameters called precision and recall, then you see that you have got an average success rate of 94%, recall of 94%, and so that is extremely good. So we wrote this paper a few years ago, and just recently, a few months ago, there was a student from IISER Tirupati working with me, Nikita Baloli, and whose job was to transfer the learning from the Sloan survey to the Subaru survey. And that was rather, that's not very easy to do. You see, the Subaru survey is very deep, and then you can see features there that you can't see in the that you can't see in the this is a picture of the Subaru survey. So you see, for example, so this is in the SDSS and this is in the Subaru. You can see features you can't see. The greatest difficulty is that there is no training sample in the Subaru because the Subaru is largely a virgin survey. Not much work has been done on it. So which means that you should be working on that, but also that is very difficult. So what the idea was that we generated this catalog using Shilu's work and then cross-correlated those catalogs with galaxies in the Subaru, and then we identified subsamples, and then we used that as a training. But then we were left with the possibility that there were no there are no test set left. So this is a very exciting problem to address. So if any one of you is interested in helping with this kind of process, so we'll be very happy to use you as a collaborator in that. So the next part is what star galaxy classification. Again, I have chosen examples which are very easy to define. So this is a old NOAO 4-meter telescope field in the optical. And then what you see here is that you see this, you see the obvious stars, you see obvious galaxies. But small little things that you see here, these dots, these are mostly galaxies. That is because this is a high latitude field. There are not many stars in this field. And now what we want to do is to be able to distinguish between stars and galaxies with good confidence. Very simple problem. So, so you see if I take an image of a galaxy, so image of a star would be largely a Gaussian profile with some complications in the edges. Uh, and then here you've got a bright galaxy. So it might appear to be like a Gaussian, but you see that the wings are quite different because the galaxy has got a totally different shape. But now look at this: it's a faint galaxy, it's a dim galaxy, and then you can't see its shape really. So how do I know what this is? Right. So 20 years ago, we tried to do this using very simple machine learning, and then what we did was that we looked at one of these plates I showed you, and actually visually identified some stars and some galaxies, and used that as a training sample, trained a neural network, and we got 98% accuracy. So I believe now that 98% was just a consequence of overtraining in the thing, and then overtraining. But those are early days. So now we are working on a more sophisticated version of it. And then you see what we have got here is that the bright gal the is a bright galaxies, and then you see that so these are medium galaxies. And then you see, look at these faint ones. And these are the ones we want to go after. And who is we? So there are 1, 2, 3, 4. These are all 4 students distributed in IISER, Bhopal, IIT Bombay, and MIT here in Pune. And then, of course, then these are Vivek from Indian Institute of Astrophysics. And no, this is, yeah, okay. And then you see, now we not only distinguish between stars and galaxies, we can also distinguish between stars and quasars, both of which have exactly the same images, okay, but they've got different colors and so forth. Okay, so now the idea is that because the galaxies are so faint, you cannot extract features from them. Okay, and then because you cannot extract features, you cannot use machine learning, and therefore you need to use deep learning. And then we have got a CNN here, a CNN architecture. And then you see, the fact is that even though we are going to use just the galaxy images, 5-color galaxy images in the classification, as it happens, the SDSS pipeline also processes each image and gives you a certain number of parameters, right? So the project students, they decided they're going to use a combination of please. Sorry, there are disturbances again and again. There is sorry. So so you see that you have got a CNN classifier here, but what the student decided is that they're going to run in parallel an ANN classifier too. Okay, and then this ANN classifier, and then you concatenate the results which you get from the two, and then you get your final classification. So here you see the beautiful feature maps, meaning that there are 3 dim galaxies, and when you pass them through the CNN filters, okay, then you get all the features which are being extracted, right? And then they carried out 3 different experiments, and because one for just the compact objects, other for faint and compact objects, and so forth. And then they have got these, because we are using a CNN, now we have got thousands and thousands, tens of thousands of images for the training, and then you make the confusion matrix, and the confusion matrix tells you what is the percentage classification. So you see that here in this experiment, we are only distinguishing between galaxies and stars. I forgot to mention one important point. Where do we get the training sample from? Because in our earlier experiment of 20 years ago, we used 20 years ago, we used visual classification. That was all right for a few hundred, but here you need training samples which are tens of thousands in size. And how do we do that? We do that by the simple expedient of using spectroscopically identified objects, and which is what Sloan tells you. You get the spectra which tell you whether it's a star or a quasar or a galaxy, and those are being used here. Okay, so you see that we get absolutely excellent accuracy, like 98% here, and then with star quasar galaxy classification, then you get 95, 91, and 93%. And one carry out detailed analysis of this, and then so we have just sent out this paper for publication, and needless to say, there'll be a lot of further work to be done on this. Then now I come to the last part of my talk. I'm running out of time. And so here we have got this is in Pune. I am the PI of a project which is known as Pune Knowledge Cluster. And then in the Pune Knowledge Cluster, the idea is to bring together various institutions and R&D labs, okay, and the industry to work for projects which are of use to the city. Okay, so these are known as, so then we have the verticals of health. We do a lot of COVID related work in health, environment, uh, and health, environment, big data and AI. And then we have got electrical vehicles and sustainable mobility. And then we do capacity building, run all kinds of courses and things like that. All right, so now as a part of this, because Professor Nainam Sajid Philip and I, we have been collaborating with a biology institute here to apply AI to their problems, and I thought that I should generalize it to an AI platform for biology and chemistry. Okay, because you've got wonderful institutes here in Pune, and there are wonderful institutes in many cities in India. The good thing about Pune is the proximity. So I'm right now sitting in the collaboration between people who are domain experts and then people like us. I mean, you have to really know how to work with each other, otherwise you wouldn't get work like this done. And the new project which you are taking up, for example, is segregation of plastic waste using NIR spectrum. So what happens here is that, I mean, let us suppose that you have connected lots and lots of plastic waste, and then you are running it on the conveyor belt, and then it goes to a detection system. And then what happens is that these plastic waste can be of completely different kinds. I would say what are the different kinds, but I mean I'm still learning there. And then the point is that you can take an infrared, near infrared spectrum of, let's say that there is a plastic bucket which is going through there, and you just take a near infrared spectrum of it. When you see an NIR spectrum, an astronomer obviously becomes very happy because we use NIR spectra all the time. And then, in fact, I've done a nice project with Kaushal Sharma and others on classification of stellar spectrum, okay, the optical and NIR. And so that can be straight away adopted to this kind of a thing. So you take a NIR spectrum and then you like train the system so that it immediately tells you, to using the spectrum, what kind of a plastic it is. And then which allows through engineering to separate, to throw it in a different bin. Other problem in the chemistry part is hydrogen transport using complex alloys. This is something which I found, I mean, I never heard of this kind of a thing, and I'm still studying it. I don't understand it very well. But the idea here is that you make up a large metal block using a complex alloy, with several different metals in it, with different compositions. And then you can fill it with hydrogen. And then the hydrogen sticks to the inside. And then you transport that block to other place, and then you take the hydrogen out there. So where does AI come into the picture? It comes in identifying the best alloy. Because if you do that chemically, then it will take forever. But there's a very great deal of data which is available. And then that data is going to be used to fix the ideal alloy. The problem with the data is that it is scattered all through the literature. There are no databases available. And therefore, we are trying to use a natural language processing based system to enter all these journals and try to extract the data. So you see that it is very interesting. Then in the biology sector, what I call heavy biology of living beings. Okay, the code chip sequences of insects. So I unfortunately did not get the time to include that video here. Maybe next time. So what happens there is that you've got these insects which are chasing each other, and if they like each other, then that could lead to mating. So the point is that you've got a video of the whole thing. It is not, you cannot view it as a set of images. It is just a video. And then you want to apply deep learning to the video to try to predict what is going to happen from this one. Okay, what is going to happen? Are they going to finally like each other or not? And the idea is that you don't care so much about the social aspect of this problem. What you are very interested in is studying the brain of the insects using this. Because I mean, if they do something, will they remember it when they see each other next and so on, which gives you insight into the way the brains of these insects are structured. Okay, so all right. Now I will end my talk in just 2 minutes, giving you examples of a specific thing, protein picking, and this also very briefly. So you have got this RNA polymerase 3 protein there, and which has got a very complex three-dimensional structure. Okay, now it is so complex that you cannot use X-ray crystallography to unravel it. Okay, so you are using you cannot use X-ray crystallography. So what the idea is the following: is that if you look at the protein from different directions, you will get a different two-dimensional view of it. Okay, so here you see you have got a protein in a substrate which is a sample, and then you put it in a grid, you freeze it, and then you observe it with an electron microscope, and then you get these things here, projections here. Each one of these, if you find a protein here, then it is a 2D projection of a 3D image. The idea is that you take all the 2D projection and put them into a map. So our idea in the problem, our part of the problem is not to construct the 3D model, but simply to identify the protein things there. Because you see this one here, and there are lots and lots of similar looking particles, but only some of them are proteins, and the rest are the substrate. So if you have a human expert, they can identify the protein. But then it takes a long time. So how do we do that? You do that using the AI system. So the idea is that first of all, you take the sample, and then you need to image process it to enhance the contrast. And then we use what is known as semantic segmentation using deep learning in the training. And then you create the training data. Okay, so that's all been done. And then you see that this is the original image. This is the contrast enhanced image. And these are the protein particles which have been identified. So when we carry out a project like this, what is required is first of all to compare it with other techniques. Okay, number one. Number two is to provide all the details and the program so that people use this in their own work. And I'm very glad to say that we are getting a lot of attention for this piece of work, and then it's been rather successful. So I'll stop there. Thank you very much.
Thanks, Ajit. It's very rare I hear a talk that goes from the scales of protein to the scales of galaxies. That was fascinating. But we are really out of time. But if there are any quick questions, please ask them now. Dibendu has a question. Dibendu, go ahead.
Yeah, Ajit, that was a fascinating overview. I just wanted to ask, given that you are also part of this Pune Knowledge Cluster, do you see specific examples of techniques in machine learning or artificial intelligence that is being evolved out of, let's say, astronomy or any scientific analysis and being applied in the industry? I mean, will the industry be interested in some of the techniques that we are using?
Yeah, you see, the industry is indeed extremely interested. I mean, I forgot to say that, but you see that the industry is an integral part of this one. So we are using the industry in the tech, in the training. For example, IBM just gave a course on AI for cybersecurity, right? And then now when you see that Sajid and I are already reaching the end of our bandwidth because there are a lot of problems here. Each problem, every single problem that I've so far done in astronomy has required a new technique because we jump from one thing to other, and the industry can be very useful there. Okay, because they can tell you that, look, I mean, we have got this software, we have got this, and we can identify it. And so we are indeed closely working with them. But on the other hand, and this is something I would like to really, really stress to all the young persons who are here, people from the astronomy side, they are going into the industry in large numbers. Let me give you an example. I mean, I'll take 2 minutes of it, but it's a fantastic example. Uh, some of you would know Dr. Avyarthana Ghosh, and she was a ICER Kolkata student, but she largely worked in here in Ayuka, and she was working with Durgesh, Professor Durgesh, then she also then she got into she was an engineer by training, so she got into making an instrument, and she has contributed very heavily to making the suit instrument for Aditya L1. After she finished her PhD, she had to find a job because she didn't want to leave Pune for personal reasons. And then I introduced her to people in TCS. What they did was that they just told her that they said that, okay, we are giving a satellite with such and such capabilities. In 15 days, you come back to us and tell us what will you do with it. So we had a nice discussion, and then we thought of various very interesting things. For example, look at all those avalanches that you have in the Himalayas, and then it would be wonderful to be able to predict them. So you have got data on the avalanches, but if you look at the ISRO maps of the Himalayas, then you will have past data on images of the same area for many years in the past. So clearly that would be a problem for deep learning to try to predict when the avalanches occur. Now she has got a nice job in TCS and she's working there. So there is going to be a movement between industry and academia, and many of you who are doing a PhD in astronomy may end up working in the industry. You should not look upon it as a punishment or the misfortune, but you look upon it as a challenge. And just like you have in Europe and the US, you need to go back and forth between industry and academia. That is where the future lies, and that is where the money is. Not only for personal things, but also for projects. Thank you.
I think that's excellent advice. Thanks, Ajit. Himapriya has a question. Maybe that's the last one. Can the faint visual features be recognized by CNN without any image processing to enhance the feature representation?
Yeah, you see, the point is that there's always this problem about signal to noise ratio. And when we do image processing, the image processing is not to touch the thing, but to remove the background, to smooth out things, etc. And how faint you can go. You see that the project which the students did, they're successful at the 90%, 95% level with galaxies which go up to the 20th magnitude. Now, beyond that faintness level, you really don't even have the training sample. So they tried one experiment. They said, let us train them or with whatever we have, and then we extend them to faint galaxies and to see what accuracy we get. And you get some 70-75% accuracy, which is really not bad compared to zero accuracy that you had if you didn't use CNN. But then I believe that this deserves to be improved. And that is where the frontiers of the field are.
Thanks very much, Ajit. The next talk is Dibendu's, but before the talk, Because of internet problems, we are kind of 5 minutes late. So Dibendu, you will have the extra 5 minutes. So we will be slightly late in finishing this session. Also, at the end of Dibendu's talk, we will have a group photo. So then we will all turn our cameras on and there will be a screenshot taken. So please bear with us. Ajit, thanks very much. We will go over to Dibendu now.
Yeah.
But if you stop sharing your screen.
Yeah, I'll do that. I was just looking for the button.
Thank you, Ajit, very much for agreeing to talk here. I think that was a fantastic exposition of what all is happening. And I'm glad you brought up this issue of moving from physics or astronomy, astrophysics to the industry, because Obutana is not the only person. In fact, one of our master students in space physics, Shreyan Shah, he recently joined uh, uh, a company in Pune, which is looking at creating artificial vision for automated cars.
Yeah.
He's also working on applying machine learning, artificial intelligence techniques. So that was also very wonderful for us. All right, let me start sharing my screen. Dhruvo, can you see my screen? And is it full screen?
You can share your screen. The next speaker is Dibendu Nundi, professor at ISER Kolkata and SESI, and he will talk about the physical origin of space weather. Dibendu, go ahead.
Okay, so I hope you can see my screen and it's moving forward.
Yes, it is. Yes, it is.
Okay, great. All right. So my talk is going to be a bit different from everything else that you're going to hear in this meeting. It's different in the sense that I'll be giving you, in whatever is possible in the next 40 minutes, a background of the physical underpinnings of space weather, starting at the sun, which is the star that governs our space environment. So the plan of my talk is, first of all, give you an understanding of what is space weather, because I understand there is a lot of undergraduate students also who are attending this workshop, primarily because they're interested in machine learning applications, but many of these people are not really aware about stellar physics or what goes on inside the sun, which generates the activity that we are trying to figure out with big data analytics. So I hope to give you a flavor of the physics of space weather, both from a phenomenological understanding of what is space weather, as well as from the physical principles that allow us to explore what is going on inside the sun that produces the activity that we are all trying to figure out. Okay, so I come from the Center of Excellence in Space Sciences. I must mention that that we have been working on applying machine learning techniques, applying computational modeling techniques, and just general statistical and image analysis techniques to understand and forecast space weather for over the last 5 years. And from last year onwards, our efforts have now gone online, where we are for the first time in the country generating routine space weather forecasts, which you can access by visiting our website, www.sesi.in/spaceweather. Okay, our textbook understanding of space, that is it's empty. There is no variations. Well, compared to the Earth's atmosphere, it is indeed empty. However, there are variations in space, and this variation is governed by the activity of our star, the sun. So it is not an unchanging empty void that you generally think about. This is a real life example of that. This is an observation from the Ooty Radio Telescope based on scintillations of stars, which is utilized to map density perturbations as they propagate from the sun through the inner heliosphere. The sun is put here as a cartoon, so is the Earth's orbit, and the Earth is here for just general visualization. The rest of the image is actual observations taken over multiple days and put together by P.K. Monoharan from the Ooty Radio Telescope. What you see here are these disturbances that originate in the sun, which are really plasma enhancements, plasma density enhancements, and they propagate outwards and through the heliosphere. What these are coronal mass ejections, which I'll talk about in some detail later. They're also part of solar wind density enhancements, which impact the Earth space environment and the technologies that are based in space. So essentially, what I want to convey to you is that our environment is an active environment which is controlled by the activity of the sun. And it is important for us to understand and predict that environment in order to protect our technologies, which is based in space. Okay, so if you look at the sun, and Shravan talked about looking at magnetograms, instruments that map the magnetic fields through the concept of Zeeman effect. And what you see here are this uh, positive and negative polarity regions known as active regions on the sun. These are sunspots which have been observed since the advent of the telescope by Galileo Galilei. We have 400 years of observations of the sunspot time series, which is the longest data series of any naturally observed phenomena in the universe, which you should be aware of. The sunspots are large structures. Their radius can be on the order of tens of thousands of kilometers, sometimes bigger than the Earth. You see them in more higher resolution image here. You see that they appear darker compared to the surroundings, and this is because the strong magnetic fields, which is about 10,000 times stronger than the Earth's magnetic field, inhibit the convective transport of energy in the interior, and that is why they appear darker. Whereas you see these convective granules on the outside of sunspots, which essentially transport the energy that's been created through nuclear fusion within the sun, and then eventually allows the star to shine. And it is this light that drives atmospheric dynamics and climate and allows life to be sustained on planets like Earth. Okay, the sunspot magnetic structures sometimes become unstable. And this is a movie put together by images from the Japanese satellite Hinode. And what you see here is this active region suddenly becomes stabilized and results in what is known as a solar flare, which is accompanied by intense high energy radiation in extreme ultraviolet as well as X-rays. And sometimes this is so energetic that it can impart enough kinetic energy to the overlying plasma in the sun's outer atmosphere and eject it out. And you see that in projection here, where you see a sort of an eruption of plasma happening out of the sun when viewed sideways. So these plasma storms, known as solar flares or coronal mass ejections, when there is ejection of plasma from the sun's outer atmosphere, contain the energy equivalent of something like 500 billion atomic explosions happening at the same time, and are one of the most energetic transient phenomena in the solar system. When we have sunspots or active regions, there is also an enhancement in the photons corresponding to X-rays and extreme ultraviolet. And these have consequences for the Earth's atmosphere, atmospheric heating, as well as for the functioning of sensitive sensors on satellites. And whenever there is a flare, there is, of course, an enhancement in this high energy photons from the sun. There is also solar energetic particles, which are accelerated in the solar flares, and they can travel almost at the speed of light and impact the sensors of satellites. And you see here a satellite being bombarded by these high energy solar energetic particles. And this can cause damage to the sensitive electronics of satellites. They can be hazardous to astronauts who are out on spacewalks outside of, for example, the International Space Station. When the solar plasma or solar energetic particles impacts the Earth's upper atmosphere, it can create this beautiful phenomena known as auroras. And these are primarily produced in high latitudes because the Earth's magnetic field lines are open at the North Pole and the South Pole, which can trap the solar energetic particles, which are charged particles. And these particles can reach the low altitudes, and they can energize the atoms into higher excited states. And when they come back down to the ground state, they emit photons corresponding to the energy difference between the excited state and the ground state. And the sky lights up in this beautiful phenomena, which is known as aurora borealis when it's in the north, or aurora australis when it's in the southern hemisphere. There are some real technological impacts of space weather, which impacts each of us and each of you, which you should be aware of. For example, when there is severe space weather, it impacts satellite broadcasts and high frequency communications. It impacts GPS navigational networks and creates inaccuracies in GPS positional systems. It also impacts air traffic over polar routes, where if you are, for example, moving from city in the north, say New Delhi to New York, you are going to fly over the poles to conserve fuel, because when you connect 2 points on a sphere, a great circle is the minimum distance, and you would like to minimize the fuel consumption and fly over the poles. The poles are very susceptible to space weather impacts because, again, of the open magnetic field lines, which allows the solar wind plasma and solar storms to reach lower altitudes. And you see here the number of flights in the polar regions has increased as our ability over time to forecast space weather has improved. Sometimes, in the most extreme cases, a geomagnetic storm induced by the impact of a solar coronal mass ejection on the Earth's magnetosphere can induce large currents at ground levels, which can take down electric power grids. And this happened in 1989, where the North American power grid went down because of a solar flare induced solar magnetic storm. And this took off the electric power grid in Quebec, and Montreal was out of power for about 3 days. So these are some very real impacts of space weather. And one often wonders whether if you're in a low latitude country like India, are you impacted? The point is you are, because India is a nation which is dependent on various satellite technologies, which are all susceptible to space weather. The solar energy output also changes with time. So, for example, what you see here on the bottom is the sunspot cycle, the sunspot time series. On the top is the total solar irradiance, which is the total energy from the sun reaching per unit area per unit time just outside of the Earth's atmosphere as measured by satellites. And you see that that is a variable and not a constant. And that variability is in fact tied to the number of sunspots on the solar surface. So therefore, the solar magnetic activity, in fact, also increases and drives changes in the solar radiative output, which is a natural driver of atmospheric dynamics and climate systems. In fact, if you could harness solar energy, in half an hour, the sun would provide enough energy to sustain the annual needs of humanity. And this tells you why there is all this research going on to develop more and more efficient solar cells to harness the power in the light of the sun. All right. How do we explore the activity of the sun? How do we characterize the space environment? There are multiple satellites, and of course, we are led into the business. But if you look at NASA, the European Space Agency, and JAXA, over the last couple of decades, we have more than 30 satellites studying the solar system, making observations of the sun's activity, making measurements of the near space environment. And this is one way that data helps us understand what is going on in terms of the origin of solar activity and how it's manifested in changes in the near space environment and what its impact on the Earth's magnetosphere and atmosphere. I may mention that India is gearing up to launch its first solar observatory, which is also going to characterize the space environment at Lagrange point L1. The Aditya L1 satellite, as it is known, will be a comprehensive mission to observe the genesis of solar storms, to observe the radiation output of the sun in ultraviolet and in soft and hard X-rays. It will also have in-situ instruments for measuring the plasma characteristics in situ or locally at Lagrange point L1, which is a point close to Earth on the Sun-Earth line, which allows you to have a continuous view of solar activity, as well as provides the opportunity to continuously downlink data so that we can have a continuous assessment of our space environment. So Deepankar Banerjee is going to talk about the Aditya L1 mission, as well as their efforts at Aries to sustain a data center and train students in the analysis of the data that is going to come out of the Aditya L1 mission. So I'm not going to talk any, in details about this anymore. Okay. So I hope that this perspective gives you the feeling that it is important to understand and forecast the sun's activity. And what do I mean by the sun's activity? It starts from understanding the origin and changes in the sun's magnetic field right from its interior to its atmosphere. Um, it involves the prediction of solar storms or solar flares, as Shravan was talking about earlier. It involves predictions and assessment of solar wind conditions, which is the background weather in the solar system, over which solar storms and solar flares act as perturbations. It involves the predictions of solar energetic particles, which can be harmful to satellites and to astronauts. It involves understanding the origin of variability in the solar radiation spectrum, and if possible, to predict the solar radiation spectrum in advance such that it can feed into models of atmospheric dynamics and climate physics. And finally, this also involves assessing the impact of space weather on planetary atmospheres and our space-based technologies, which we are critically dependent on. All right. The first step in all of this, of course, is to understand the magnetic field output of the sun or the cycle of sunspots, which govern much of the other variabilities in the space environment that I just discussed. Okay, so now I will dive into the physics of the system and try to give you a sense of why this is a very challenging task. So what are we looking at here? You're looking at a domain that is extremely vast. We are used as physicists to look at laboratory scale physics. We are used to small atomic scale physics. But here we're talking about the interior of a star which is far away. One astronomical unit is about 10 to the power 11 kilometers away from the Earth. We're talking of understanding the physics of how activity is generated in the interior of that star, which is the sun. We are talking about, yes?
There is a question.
Yes. Can you please read out the question?
Are there any precautionary measures to avoid this problem from solar storms?
Okay, so the only precautionary measures that you can actually take in terms of satellites is putting them on what is known as a parking mode, so that you protect the sensitive electronics inside from damages that may happen during solar flares. There certainly isn't any way that can stop them. So advanced warning systems are useful in mitigating the impacts of it. So that's why it is helpful. All right. So starting from the inside of the sun, you go to the exterior of the sun, where much of the dynamics plays out in terms of the coronal magnetic fields generating the solar flares and coronal mass ejections. And then the solar wind takes over from near the sun all the way to the solar system. And it's the solar wind, the radiation spectrum of the sun, and the variable perturbations in terms of the coronal mass ejections, which are high density plasmas compared to the solar wind containing magnetic fields, which then impact planetary magnetospheres. So a system-wide understanding requires understanding of the physics and predictions across the solar domain. And I would like to emphasize that this is important because this knowledge that you gain from the solar system can be carried over to understand exoplanetary systems and habitability, or what makes exoplanets habitable, in conditions which are governed by the parent star. So we really live in an astrophysical ecosystem. We cannot be separated from the universe that we live in, from the star around which we orbit. And I want all of you to go away with that idea that human existence is not in isolation. We share an universe, an ecosystem with the universe that is constantly changing and that is impacting us from time scales of days, which is space weather, to millennia and billions of years, governed by the evolution of the star and the cosmos. The physical domains are very distinct because inside the star, you're dealing with a very high density plasma system. So you're dealing with a high plasma beta system, whereas in the exterior of stars, you are dealing with a low plasma beta system, which is a very low density system. And then when you are far away from the star, the solar wind dynamic pressure takes over and the plasma starts dominating again. And so again, you are dealing with a high plasma beta system. And so modeling or understanding them together is a highly challenging task. But I'll try to give an understanding of how we do it as we go along. Okay, so let me talk about the interior of stars. So stars like the sun are made up of plasma, and this is because they're sustained in the stable state to the main sequence lifetime by nuclear fusion reactions, which create a pressure gradient and a force due to the pressure gradient, which can balance the inward attraction of gravity, holding the star together. This also implies quite a bit of energy is being produced in the interior, and this energy ionizes the atoms inside of stars, and essentially what you have is a completely ionized matter, which is plasma existing inside of stars in the inner part of the star like the
Dipendu,
sun. Yes.
quick question.
Right.
What is plasma beta?
Okay, plasma beta is the ratio of the gas pressure to the magnetic pressure, and I will talk about it in great detail later on, so therefore I really zoomed over it earlier. Okay, so the interior starts like the sun. The energy is first transported by radiation through multiple absorption and radiation of photons. Subsequently, when you hit the base of what is known as the convection zone, the plasma becomes opaque to radiation. And so it absorbs the photons, which hits up the plasma and makes it lighter, and therefore it sort of rises up against gravity, and that motion carries the heated plasma up to the surface where the excess energy is radiated out in terms of the light that you see from a star. This allows the plasma to cool and become more denser, and it sinks down. So there is this up and down motion in the outer 30% of the sun, which is known as convection, which happens also in the Earth's atmosphere and also happens in a teapot, except here we're dealing with the convection of or motion of ionized uh, 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 particles or atoms which have been ionized. So essentially, you are dealing with large electric current systems which can produce magnetic fields. And essentially, it's in this region that the field of magnetohydrodynamics becomes relevant, which is the dynamics of magnetized plasmas. Um, to understand this, we can begin with the Maxwell's equations and formulate what is known as the magnetic induction equation under certain approximations of a non-relativistic plasma, and assuming that the plasma is a single fluid charge neutral model, which then in conjunction with the Ohm's law, uh, you can essentially get rid of the electric field and write down an equation in terms of what is known as the magnetic induction equation, which is out here. So the magnetic induction equation tells you the magnetic field B varies in space with time given certain plasma velocities, which is identified here by V, and a diffusion of the plasma, which is identified by this parameter eta. Now, of course, along with this, you have to maintain the divergence of B condition, where, which essentially implies that flux is conserved in such systems. Okay, to describe the motion of plasmas, you also need to have an equation for the velocity field. And this is the famous Navier-Stokes equation.
I don't hear anything. Does anybody else do?
I think there is some problem from Dibyendu's side.
Okay, so there is some problem, and I believe Dibyendu will join in a
Yeah,
minute.
yeah. Just wait for.
The Bendu has somehow got disconnected, so we are waiting for him to come back. Did we predict a solar storm that was supposed to take out the internet? So we are trying to call the Bendu over phone. Bear with us. I guess these are the slings and arrows of an online meeting. While we are waiting, maybe it's a good time to mention about the afternoon session. So maybe the LOC can mention exactly how the afternoon session will be run and where everybody is supposed to be. I believe everyone who is in place in ISAR should be there in the computer center, and those who are doing it online should do, I'm not sure in exactly what
Yeah.
way.
Yeah, those who are in either campus, the either students, they can come to computer center CC1 in the AAC building first floor for this session. This will be done in the hybrid mode. So, and those who are outside the either campus, so they can remotely join from anywhere. So that's the plan. So that will be start from 2 p.m. to 5 p.m. So yeah, that's we can have a photo session in that case. I mean, as many of us, all the people are not here, so we can have one photo session for now. I mean, then we can have another maybe later.
I think that may not be a bad idea. Let's do that.
Yeah.
So
So
please turn on your cameras so that we can take a photo. Ashwin, can I answer that later about the certificates? So rest of you, can you please turn on your cameras? But some of you may not have the rights to turn on your cameras.
just I'm giving the. Now everyone should yeah. Can do.
Yes, but how do you fit about 60 people on the same screen? I have no clue. Prashanjit, do you know how we are doing this? Okay, I don't know when to call for cheese.
Yeah, so I'm the guy who's taking the photo,
And
and
the
the
expectation
screenshot
that you can
basically,
change the layout to tiles.
yes. There's a glitch that in even in tiles you only can have 50 people.
Okay.
So I'm trying to figure it out, but for the now on, let's take the first 50 people that I am getting, and meanwhile I'll
Okay.
try to figure out, as I mean, there is a software that can add more people in
Okay.
the slide. So for now on, let's take a picture of the first 50 people that I am getting.
Okay. Ajit,
Okay.
can you bring the camera down a little bit? Yes, that's better.
Okay.
Excellent.
Yes.
Yes.
Yep. So so cheese, everyone. The cheese. Another one.
More cheese.
More cheese. Maybe some paneer also.
Okay,
Yeah,
so
I'm
now,
done. I'm done. Thank you.
but should
So
some of us turn off the camera that you can take a rest of us?
no, yeah, I'll that's a better idea, I think.
Okay, so let me turn off my camera, and but if everybody does that, then that's not
Then
really-
there's the see, I'm finding another way to solve this glitch, but for this time, let's take another one. So those who are turning on their camera, please say cheese. Yes, it's done. Thank you all. Probably I'll ask you again to turn on your camera once I find the way to fit everyone in the screen.
So actually, this is about the time we were supposed to end, but we still have an internet glitch. So I don't know what is the best choice to take. Maybe we wait for 5 minutes, and if we still can't find the Bendu, we will stop for today and then schedule part of his talk tomorrow in the morning. Shovik, will you please let me know when your picture taking is done?